Welcome to lecture 2. So let's continue our topic on the stereospecificity of E2 reactions. So I already discussed that in E2 reactions, either the reactions are stereospecific or they are stereoselective. So when the reaction is stereospecific, then each of the products will yield only one. So each of the reactants will only yield one product. And in a stereoselective reaction, you can have two products that form. You have a major product and a minor product that form at the same time. So this here is the example of stereospecific part, so which means that you only form one product. So this is a reaction where it selectively chooses the one that has a proton. So the proton now here is, this is the alpha carbon and this is the proton part. So there's only one proton here. So, and there's another one here. So it always chooses the one that has more substituted carbons. So this side is more substituted, so it chooses this side, resulting in the product formation here. So here it's a E2 reaction. So understanding the difference between the two reactions is really important. Why is it the case? So only one of the alkyl halides undergoes E2 elimination much faster than its diastereomer. So why is there a difference in the reaction rates here? So this comes under the topic of E2 reactions, substrates, and the difference between stereoselective and stereospecific reactions. So there are many factors to consider in order to correctly predict the products of an E2 reaction and decide what the major products will be. So will the substrate react stereospecifically, or will it react using a stereoselective mechanism? Second question is, will the substrate produce several regioisomeric alkenes? If so, what will be the major product given the steric hindrance of the base that is used? And third, the only way to master this skill is to do a lots of practice problems. So let's start with so this is how we generally differentiate between E2 reactions and E1 reactions. At the end of this lecture, we'll talk about how to predict the product of what mechanism it works through. Next, let's talk about unimolecular reactions. So unimolecular reactions involve stepwise reactions or stepwise mechanism. So consider the following reaction that we have here. So where you have a substitution and an elimination product. So you have a tertiary alkyl bromide and you're using ethyl alcohol as the solvent. You end up getting a substitution product and an elimination product. So notice that the substrate here is tertiary. So the chances are SN2 substitution will not be occurring because SN2 substitution requires less steric hindrance. So the more steric hindrance there is, the chances of having a unimolecular reaction is negligible. Sorry, the SN2 reaction is negligible. So the reagent is ethyl alcohol, which is not a strong base. So E2 elimination is generally unlikely. So you cannot have SN2, you cannot have E2. So it turns out that the formation of substitution and elimination products follows first order kinetics, which confirms neither SN2 nor E2. So these reactions where only one of them is required to determine the rate of reaction is called as unimolecular reactions. So what happens in this mechanism? So the mechanisms of both substitution and elimination here start with the exact same step. Is the first thing that happens is the ionization of the substrate. So what happens first is you lose the leaving group and you end up with a carbocation intermediate. So this is one of the most important steps that you see in unimolecular reactions. So remember that this is actually an intermediate. So remember that intermediate is a substance that actually forms and that actually has a certain amount. Now once it creates the carbocation then decides whether the reaction will undergo substitution or elimination. But until this step in both of the reactions, it's common. So the common step is the same for both of the reactions. Now after the carbocation here is formed, it will undergo substitution or elimination, and depending on how it reacts with the solvent. So here let's take an example. You have the loss of a leaving group. You lose the Br minus, you have a carbocation. The hydroxy group on ethyl alcohol will attack the carbocation. This creates the nucleophilic attack. Once the nucleophilic attack occurs, what happens here is the positive charge takes up the electron pair and bonds with the oxygen. Oxygen gets a positive charge. Now there is excess amount of protons on this, it undergoes proton transfer by the attack of another ethyl alcohol molecule, resulting in a substitution product. Now the entire mechanism here is actually in 3 steps, but the last step is a proton transfer. We do not consider that as a single step, but there are 2 main steps in this attack. The first step is the loss of a leaving group, creating a carbocation intermediate, and second step is the nucleophilic attack. So these are the main 2 steps that are involved. This process is called solvolysis because the nucleophile is also the solvent. Remember, this mechanism is that the nucleophile itself acts as the solvent. So we do not use a separate solvent again. The solvent itself acts as the nucleophile. So in SN1 reaction coordinates, in terms of the determining step, which determines the rate of reaction, the first step is the rate of reaction is determined by the formation of the carbocation. So the substrate, how much amount is the amount of carbocation intermediate formed, is the one that decides the rate of the reaction. Here the first peak is the loss of leaving group and the second peak is the nucleophilic attack. The first crest here, the first dip here, involves the formation of the intermediate here. So this is the energy diagram for an SN1 reaction. So here you only need the substrate to determine the rate of reaction, because unless the substrate creates the carbocation, the reaction will not occur. So the formation of the carbocation here itself is the one that determines the rate of reaction of this process. So it is clear here that when substitution occurs via the carbocation intermediate, we call this SN1. The reason why we call it SN1, the 1 here says that there is only one molecule that is important in determining the rate of the reaction, so that is the substrate itself. In SN2 you need both the substrate and the nucleophile, but in SN1 reactions you only need the substrate itself to determine the rate of reaction. And SN, obviously S represents substitution and N represents the nucleophilic step. So what is the SN1 mechanism here? First, you have the loss of leaving group where you lose the halogen and you create a carbocation intermediate. Then the nucleophile attacks the positively charged carbocation and finally results in the substitution product. So this here, remember that the nucleophile here is a neutral species such as an alcohol. There will be a proton transfer after the nucleophilic attack. So next let's talk about E1 mechanism. So again, the mechanism involves the same thing, the loss of leaving group. So the elimination reaction of a tertiary substrate in an alcohol solvent like ethyl alcohol also proceeds through a 2-step process. First step is again the removal of the leaving group, so loss of leaving group. And the second thing that happens is that rather than a nucleophilic attack, the base that you use ends up attacking the beta hydrogen and eliminates the beta hydrogen, resulting in the formation of the elimination product. Here the ethyl alcohol serves as a base but not as a nucleophile and deprotonates the carbocation to form an alkene. So like SN1 mechanism, so the E1 mechanism is also unimolecular and it also follows the same kinetics as any other reaction. So here also E1 kinetics involves the same product, but the difference between both E1 and SN1 is they have the same rate determining step, which is the formation of the carbocation. But SN1 is more favorable because SN1 produces lower energy products than E1 reaction. So this is the reaction that you end up with. But one of the main important points to remember in SN1 reactions is that SN1 and E1 reactions proceed through a carbocation intermediate, which means here that the carbocation may undergo a hydride or methide shift, where the positive charge can move towards the most stable carbon, which means it goes towards the more substituted carbon. That requires the movement of the hydrogen from one point to the other point. So you can have an SN1 product and you can have an SN1 product with a hydride shift. So this here is an example of what you can see in terms of rearrangements. So when you have a reaction like this here, this involves only one SN1 product, but you do not observe this product here. The reason you don't observe this is mainly because the carbocation already has shifted towards the most stable carbon before you start the reaction. So once the reaction happens here, once the product leaves here, the positive charge will move towards the most stable carbon. And because the positive charge moves towards the stable carbon, you only end up with one single product. Now, so the experimental data here indicates that SN1 and E1 reactions are generally faster when you have a polar protic solvent. So remember this, when you have a polar aprotic solvent, the reaction that occurs is SN2 reaction. When you have a polar protic solvent, the reaction that occurs is SN1 reaction that gets favorable, and it's also favorable for E1 reactions. So molecules like water, methanol, ethanol, acetone and diethyl ether are common compounds. Acetone and diethyl ether are polar aprotic solvents, so these do not undergo they do not have any protons to donate, but water, methanol and ethanol are generally products that generally undergo a good amount of SN1 and E1 reactions. So overall, for SN2 reactions, you need a polar aprotic solvent. For an SN1 reaction, you need a polar protic solvent. So that's how you can decide on the structure. Now, in terms of the substrate, the better the leaving group, the faster the SN1 or E1 reactions. So the rate determining step for SN1 and E1 reactions is the ionization step, which is the formation of the carbocation. So the more stable the halide ion, the faster the ionization. That is the reason why it undergoes a hydride shift. Now, tertiary carbocations are generally the ones that undergo really fast reactions. That's why tertiary alkyl halides are more favorable for SN1 and E1 products. Primary and secondary alkyl halides are generally too slow to observe the formation of SN1 and E1 products. So you can observe tertiary alkyl halides having this reaction. You can have benzylic and allylic halides that undergo solvolysis at a practical rate. So SN1 and E1 in terms of the substrate, so you should be able to judge whether or not a given alkyl halide will undergo the solvolysis reaction. So in general, a primary or a secondary alkyl halide will only undergo solvolysis if there is a rearrangement to a more stable cation. So remember that rearrangement is very important for the carbocation to undergo the reaction. So that would be the step that gives the additional activation energy for the reaction to occur. So tertiary allylic and benzylic alkyl halides will undergo solvolysis to give a mixture of SN1 and E1 products. So you get both SN1 and E1 products at the same time. So like we saw in E2 elimination, it is also possible for E1 elimination to yield more than one regioisomer. You can have the Hoffman product, you can have the Zeiser product. So the same thing happens in E1 reactions as well. But E1 reactions will always give the most stable alkene, which will always be the major product, which will be the most substituted alkene. So E1 reactions also favor the Zeiser product formation. So E1 reactions are also regioselective, but we cannot control the regioselectivity like we can with E2 reactions. So in E2 reactions, there is a chance of regioselectivity, but here we cannot control the regioselectivity in E1 reactions. So in terms of the stereoselectivity, again, we end up with 3 different isomers in terms of the elimination product, provided all of the isomers will form, and E1 reactions will give you the most stable alkene as the major product. So when you have 2 stereoisomers are obtained, the least sterically hindered isomer will be the most stable one. So E1 reactions are generally stereoselective. So what happens here in terms of stereoselectivity? The bromine here, once it leaves, the chances of the nucleophile attacking are the same on both sides, which means that you can get either inversion of configuration or retention of configuration. Remember that in SN2 there is 100% inversion, but in SN1 there is 50-50 chance of having both inverted and retained structure of the molecule. So more commonly it tries to put more inversion, because the chances are that the nucleophile will not attack towards the side where the bromine lives. So inversion is more common than retention. So this is the idea behind the reaction. So next, let's talk about predicting the product. So when you look at a reaction, we have all the factors. When you have clear factors that require the product formation, when you have a alkyl halide reacting with a nucleophile or a base. So it should also be that in many cases that you can get a mixture of substitution or elimination products. For example, if you take the reaction, you can get E2 products as well as SN2 products at the same time. So it's also possible that some products will only give one single product. So how do you predict the products then? The first step is to determine the function of the reagent. The second step is to analyze the substrate and determine the expected mechanism. The third step is to consider any relevant regiochemical or stereochemical requirements. So the first one is the reagent. Let's start with the reagent. For SN2, you need a strong nucleophile. For SN1, you need a weak nucleophile. For E2, you need a strong base. For E1, you need a weak base. There are chances that some nucleophiles are good bases as well as good nucleophiles. So let's classify these reagents based on the basicity and nucleophilicity. So sodium hydride, dibutyl, diisobutyl nitride and DBU are strong bases, but they are weak nucleophiles. OH minus, MEO minus and OET minus, these are strong bases and strong nucleophiles. All the halogens and all sulfides are generally very weak bases, but they are really strong nucleophiles. And H2O, methyl alcohol and ethyl alcohol are weak bases and weak nucleophiles. So a strong base and a weak nucleophile always favors the E2 reaction. A strong base and a strong nucleophile will favor SN2 and E2. A weak base and a strong nucleophile will always favor the SN nucleophilic substitution and both SN1 and SN2. A weak base and a weak nucleophile always substitutes for SN1 and E1. Remember that SN1 E1 reactions are only possible when they have a weak base and a weak nucleophile. So in terms of their prime, we can classify the reactions based on the structure. If you have a primary alkyl halide and a strong base and a weak nucleophile, you end up with an E2 reaction. When you have a strong base and a strong nucleophile for a primary alkyl halide, the major product will be SN2, the minor product will be E2. But when you have a strong nucleophile and a weak base, the primary alkyl halide will only yield SN2 reaction. Primary alkyl halides do not react with weak base, weak nucleophiles. In terms of the secondary alkyl halides, when you have a strong base and a weak nucleophile, only E2 products will form. When you have a strong base and a strong nucleophile, E2 will be the major, SN2 will be the minor. When you have a weak base and a strong nucleophile, only SN2 reactions will occur. Now, for tertiary alkyl halides, there is no SN2. You can completely forget that there is no SN2. Now, when you have a tertiary reaction and a strong base weak nucleophile and a strong base strong nucleophile, only E2 reactions will occur. For a tertiary alkyl halide with a weak base and a strong nucleophile, SN1 reaction will occur. But a tertiary alkyl halide with both weak base and a weak nucleophile, you end up with 50-50 chance of having SN1 and E1 at the same time. So this is the idea behind the reaction. Next, let's talk about regioselectivity or stereoselectivity. Now, once you have analyzed the reagent and the substrate, you can say which mechanism will occur. Now you can draw all the possible regio and stereoisomers and then finally choose the major using the guidelines that you have learned right now. So let's start with SN2. For SN2 reaction, you will observe a single product, which is going to be the inverted configuration at the alpha carbon. So you're going to see a nucleophile that attacks the alpha position and the leaving group will be connected, and this leaving group results in inversion of configuration. When you have an E2 reaction, the first thing you have to do is try to draw all the possible alkene isomers and choose the one that results from a beta hydrogen anti-periplanar structure to the leaving form. Now, if you have a bulky base, the Hoffman product will be the major one, which is the less substituted product. So when you have a non-bulky base, the most stable alkene will be the major one, which will be the most substituted alkene. So remember the difference. When you have an E2 product, the Zaitsev product is favored over the Hoffman product unless we use a bulky base. Next, for SN1 reaction, always first draw the carbocation intermediate and consider if it will rearrange. If not, then attach the nucleophile to the carbocation. If it rearranges, draw the resulting carbocation, then attach to the nucleophile too. So first, if a chiral carbon is found by an attack of the nucleophile, then you have two products, both R and S, and draw them both. Next, for E1, draw the carbocation first and from the loss of leaving group. Now, if it undergoes rearrangement, draw the rearranged carbocation. Then draw all possible alkene isomers resulting from the elimination of the beta hydrogen, and all possible alkene stereoisomers will form. Remember that E1 is not a stereospecific reaction, it forms every single product, but you will only have the major product. The major product will be the most stable alkene, which would be the Zaitsev product. So Zaitsev product is favored for E1 reaction. So let's take a reaction here, and they're asking us to predict the product of the following reaction. So you have the product here and you have NaOH. So NaOH is a really strong base and it's also a strong nucleophile. So which means that you can have both SN2 and E2 will be favored. Now the next step that we need to look at is the substrate. The substrate here is a secondary alkyl halide. Notice that the alpha carbon here is the secondary alkyl halide. So both SN2 and E2 will occur, but here because it's secondary, E2 will be the one that dominates, because secondary substrates are generally hindered and backside attack is generally more difficult. Now what would be the SN2 product here? It undergoes inversion of configuration, so whatever here is in the forward one will go to the back, and in place of Br you will be replaced with OH. So this is the SN2 product. In terms of the E2 product, we have to draw all the beta hydrogens. All the beta hydrogens are, so this is the alpha carbon, this is one of the beta carbons, this is the other beta carbon. Now after you eliminate the beta hydrogens, so these are all the products that you end up with. So now let's try and understand all the products that you have. First product that you end up with is elimination of this hydrogen here. Once that elimination occurs, you end up with the double bond between both the alpha and beta carbon. Now the chances are you can have elimination of HA. When you eliminate HB, the chances are it undergoes an inversion in configuration. So this is the trans product that you get, and this is the cis isomer, cis alkene that you get. So which means that this is the, so you have the E isomer and you have the Z isomer, and once you eliminate one of these hydrogens here, that results in this product here. So this is one class of products with elimination of beta hydrogens. This is the other class of product with elimination of beta hydrogen. So now which will be the one that ends up forming most? The E isomer is the most stable one, and the E isomer will be the most stable alkene. And you will still get SN2 product, but it will be the minor product. So out of them, the major product out of all of the isomers that form is the E isomer. So this is how you can consider the step. Next, let's talk about final one, alcohols. Alcohols can also be used in substitution and elimination reactions, and they can also be used as starting materials to make alkyl halides and alkenes. So when you use a primary alcohol and combine it with any hydrohalic acid, it creates a hydrogen halide and water. Now we need strongly acidic conditions to do these reactions, because the problem here is that OH is a really bad leaving group. So to make it a good leaving group, first thing that we need to do is we need to convert that OH into a H2O, which means first the alcohol undergoes a proton transfer, taking a proton from the hydrohalic acid and resulting in the formation of H2O, and the H2O, once it leaves, the bromine attacks under SN2 reaction and forms the alkyl halide. Now alcohols also, when you have a tertiary alcohol, it undergoes, so the mechanism will either be SN1 or SN2 depending on the substrate. So primary alcohols always react via SN2 reaction, but secondary and tertiary alcohols react via SN1 reaction. So for you need really strong acidic conditions or protic conditions which would favor SN1 reactions. Remember that primary carbocations are too unstable to form, so primary alcohols always react via the SN2 mechanism. Now alcohols will undergo E1 elimination when you react it with H2SO4. So it undergoes E2 elimination when you have concentrated H2SO4. So this is a process by which we can create alkenes. The reverse process is dilution. Dilution of a tertiary alkene can create dilution of an alkene can create an alcohol as well. So this is the opposite mechanism which we'll learn in alcohols and phenols. So what are the synthesis strategies we have? We started with a primary halide. When you use NaOH, you can produce an alcohol. When you want to produce the alkyl halide, we use hydrohalic acids. When you use sodium hydride or turbidyl potassium oxide, so potassium turbidoxide, you can produce an alkene. When you use tosylates, tosylates are basically other versions of alkyl halides. This can also act as a nucleophile. That can also produce an alkene. When you use sodium methoxide, it produces ethers. When you use sodium thiols, it can produce thiols here. When you use acetic acid, it produces esters, and when you use sodium cyanide, you can create nitriles. So these are all the processes that we can use and convert a primary halide into different functional groups. Now when you use a tertiary alkyl halide, remember the reactions here. When you use water, it becomes an alcohol. When we use concentrated H2SO4, you can create the Zeiser product. When you use turbid oxide, it can create a Hoffman product. So these are some of the products that you can end up with. So when thinking about how to make something, we first think about what is the finished product will look like. So think about it like, imagine it like we are building a brick house. So we have to first imagine what the house will look like. Then we decide what bricks would be needed to use it. So organic synthesis is also uses the same method. So we call this approach the retrosynthetic analysis. So this is something that you're going to learn about it as we go through the lectures. So what do we do in retrosynthetic analysis is, for example, let's say we have to synthesize this particular product. First thing we need to identify is a bond in the target molecule that can be made using a reaction that you know. So first thing that we know is that we can break this reaction and you can make this product from sodium ethoxide and alkyl bromide. The SN2 mechanism results in the ether formation here. So this is an example of a retrosynthetic arrow. This is the arrow that we are basically saying that we are thinking backwards. Now, so here we have the second mechanism that we can use in SN2 mechanism is we use an alkoxide ion and an alkyl bromide. So this is the process. These are the two processes that we know. And third thing we need to know is verify that the reaction that you have proposed is reasonable or not. So first we have primary halide and a strong unhindered nucleophile. So you have to remember that both should be good for SN2 reaction. When both are good, then we can draw the final reaction and write down the final product. So this is how the process of retrosynthetic analysis works. So use the same principle, try it on your own. If not, just leave it out, but try it on your own and see if you can guess which product where do we start for this product formation. So with that, we end our lecture on alkyl halides, nucleophilic elimination and substitution reactions.